Have you ever wondered why milk goes sour in summer or why iron gates turn reddish-brown over time? These aren't just random accidents, they are the universe rewriting its own code through chemical reactions. This lesson isn't just about memorizing formulas, it's about decoding the language of change that governs everything from the digestion of your lunch to the rusting of a bridge. We are going to look past the surface and understand how and why new substances are formed. Let's start decoding the secrets of matter. Look at the world around you, from the grapes fermenting in a barrel to the food cooking on your stove. In every single one of these scenarios, the identity of the original substance is being completely transformed. It's not just a physical change like melting ice, it's a chemical identity crisis where new bonds break and form to create something entirely new. Whether it's respiration powering your cells or milk spoiling on the counter, a chemical reaction is the invisible engine driving these changes. Imagine holding a strip of magnesium metal. It looks dull and ordinary, right? But burn it, and you get this blinding, dazzling white flame that leaves behind a pile of white ash. That ash isn't just burnt leftovers. It's magnesium oxide, a completely new compound born from the metal reacting with oxygen in the air. This simple experiment is our first solid proof that a reaction has occurred, changing a shiny metal into a powdery white solid. Chemistry is a bit like a magic show, but the secrets are real. When you mix clear lead nitrate with potassium iodide, boom, a vibrant yellow solid instantly appears out of nowhere. That's a precipitate, a solid falling out of a liquid solution. And look at the flask with zinc and acid. Those bubbles are hydrogen gas escaping, and if you touched the glass, you'd feel heat. These dramatic changes in color and temperature are the universe's way of waving a flag to say, hey, a reaction is happening here. How do you play detective in the atomic world when you can't see the atoms themselves? You look for the fingerprints they leave behind. A change in state, a sudden shift in color, the release of gas, or a temperature swing. If you spot any of these 4 signs, you can be sure a chemical event has taken place. It's a simple checklist, but it allows us to identify reactions happening in a test tube or even inside a star. Describing a reaction in a full sentence, like magnesium burns in oxygen to form, is exhausting and clunky. Scientists love efficiency, so we use a shorthand code, the chemical equation. By swapping words for chemical formulas, Mg for magnesium, O2 for oxygen, we condense a whole paragraph into a sleek, readable line of code. Mg plus O2, MgO. It's the universal language of chemistry, allowing us to see exactly who the reactants and products are at a glance. Wait a second, look at the scale. We have 2 oxygen atoms on the left, but only 1 on the right. That breaks the golden rule of the universe, the law of conservation of mass, which says you can't create or destroy matter. An unbalanced equation is like a lying receipt. It doesn't account for everything you started with. To be scientifically honest, we must balance the scales so the number of atoms before the reaction equals the number after. Balancing an equation is a logic puzzle. You can't change the boxes. That would change the identity of the chemicals. So you have to adjust the numbers in front of them. Start with the biggest molecule, like the iron oxide here, and work your way down to the single elements. It might take a little trial and error, adjusting the coefficients for hydrogen and iron, but eventually, everything clicks. When the atoms on the left match the atoms on the right, you've successfully respected the laws of physics. A recipe isn't helpful if it doesn't tell you whether to use ice or steam, right? That's why we add state symbols like S for solid, L for liquid, G for gas, and AQ for aqueous solutions. We can even write conditions like sunlight or chlorophyll above the arrow to show exactly what's needed to make the reaction go. This transforms a skeletal equation into a detailed instruction manual for recreating the reaction. Think of chemical reactions as relationships. A combination reaction is like a marriage. 2 separate reactants, like calcium oxide and water, join forces to create a single new product, releasing a lot of passionate heat in the process. On the flip side, we have decomposition, which is the breakup. A single compound, like ferrous sulfate, falls apart into smaller pieces, usually requiring energy to force them apart. One builds up, the other breaks down. Breaking bonds isn't easy. You need energy to do it. We can use heat, thermal, to break down limestone for cement, electricity, electrolytic, to rip water molecules apart into hydrogen and oxygen, or even light, photolytic, to decompose silver chloride. That last one is actually the secret behind old-school black and white photography. Whether it's heat, sparks, or sunlight, these endothermic reactions suck up energy to drive the change. Here we have the drama of displacement. A strong reactive element like iron kicks out a weaker one, copper, taking its place in the solution and changing the color from blue to green. Then there's the double displacement, which is more of a partner swap. Ions exchange partners between two reactants, often creating an insoluble solid precipitate like barium sulfate. It's a dance of atoms where reactivity determines who ends up with whom. This is the grand exchange of chemistry, often called redox. Imagine oxygen is a currency. If you gain it, you are oxidized, but if you lose it, you are reduced. In this reaction, copper oxide loses its oxygen, reduction, while hydrogen gains it, oxidation. They are two sides of the same coin. You can't have one without the other, proving that chemistry is always a zero-sum game of electron and atom trading. Oxygen keeps us alive, but it's also a relentless attacker of metals and food. Corrosion is the slow eating away of metals, like the rusting of bridges or the green patina on copper statues, costing us billions in repairs. Rancidity is what happens when oxygen attacks the fats in your chips, making them smell and taste terrible. That's why chip bags are puffed up with nitrogen, to act as a shield against this invisible oxidation attack. So we've cracked the case. We started with clues like color changes and gas evolution, decoded the symbols of chemical equations, and categorized the suspects into types like combination, decomposition, and redox. We even saw how these invisible atomic shifts cause massive real-world effects like rust and spoilage. Keep your eyes open because these chemical plot lines are playing out all around you every single second.